Okay. Can you all see the slides?
Yes, sir.
Hello. So again, quick check. Pointer on the left side.
Yes,
Yes,
sir.
sir.
Yes, sir.
Top.
Yes, sir.
Right.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Let me just quickly go to the point where we stopped last time. I think last time we were talking about the factors that we have to keep in mind when we are trying to optimize the fermentation process or optimize the design of the fermenter itself. Okay, and we had looked at how uh, using the correct strain and using a high yielding strain or developing a high yielding strain is probably the most important factor. Given that, we also look at how the effect of conditions of growth on the growth curve also play a big role in the productivity. In that, when we try to do fermentation, we try and make sure that the organism spend the maximum time in what is called the productive phase of the growth curve. We also looked at the fact that the shape of the cells and the size of the cells have a bearing in how you do the fermentation. For example, as we said, that animal cells or what you call as uh, eukaryotic cells are very, very fragile. And in the same breath, bacterial cells or plant cells have got much more robustness. And they have a cell wall. Plant cells have a cell wall, so they can bear a lot of forces more comfortably. We also said that organisms which are filamentous create a lot of problems, and when you are trying to stir the medium or shake the medium. We also looked at the size and scale of process, and we said that fermentations can technically be done at the lab scale or pilot scale or even the industrial scale depending on the volumes. Okay, and we said that things like up to 10 liters is what we call as lab scale, maybe 10 to 100 to 200 liters is pilot scale, and then things which are in the range of 50,000 liters, 100,000 liters, or even more than that, we call it industrial scale. And then depending on the product, you could work at every level. And what is important is that each level, the way we manufacture and way we control the processes and the considerations can be very, very different. Okay, and we closed with how we sterilize medium and air, and we said that typically medium is sterilized in most of the cases in the fermenter itself by I think using jacketed or coils to heat up the medium, or by passing steam to heat up the medium. Okay, and it said that generally if you are passing steam to heat the medium or autoclave the medium, then you make mediums which is slightly more concentrated because of dilution, because of steam condensing when you are passing through it. And then after you allow it to be at the correct temperature for the correct time which is required for sterilization, then you make up the volume and then you have sterile medium. In the same breath, we said sterilization of air is typically done using what are called as filters or high efficiency particulate air filters, which have a pore size such that they will not allow bacteria to go through. Okay, what we call as 0.22 micron pore size. So when air is passed through these filters and then it is used for aeration, for example, then there is no contamination due to air which will occur as far as the medium is concerned. Okay, so we are at this point, and now what we'll do is talk about the next aspect, which is aeration, agitation, and baffles. Okay, so as we said that there are some processes which necessarily are aerobic. Okay, and if they are aerobic, you need to actually pump in air so that the process occurs, without stoppage. Uh, and the other thing is, even when you do anaerobic fermentations, you still need to stir the medium so that there is this good interaction between the components of the medium and the organism itself, so that nutrients can go efficiently to the organism, metals, ions, micronutrients, they go correctly into the organism, so the organism can take them up, use them to grow comfortably and grow nicely, so that your yields are very high. Okay, so agitation of the medium is a common feature whether the fermentation is aerobic or anaerobic. But given the fact that the fermentation is aerobic, then another aspect also comes in, that you need to do aeration. Okay. In fermentations which are aerobic, many times the design of aeration and agitation systems are done kind of in together, in tandem, realizing that both of these are required. And in case of anaerobic fermentations, the only worry we have of is generally agitation. Okay, but how do we do this? Okay, and there are different types of agitators, or what are called as mixers, that are available, uh, and what you use depends actually on how efficiently you want the mixing to occur. Okay, now the idea of using this agitator is, as I say, one is to make sure the gas phase and the fluid mix, so that air will dissolve in the medium, and only when air dissolves in the medium, that the medium contains air which can be taken up by the organism. So what is called as air dispersion. And as air dispersion occurs, oxygen will also be transferred into the medium, which can be taken up by the organism. The second thing is, sometimes when you are doing fermentations at temperature which are not room temperatures, you need to heat up the fermenter, and generally this is done by passing hot water in the jackets or hot water into the coils. When you do that, only the liquid which is near the jacket or near the coil will get heated, but the rest of the medium also has to get the heat, and in order to enhance what is called as heat transfer, again you need to mix the medium. Okay, so then again, when you have a lot of suspension of solid particles and you're doing slurry type of fermentation, the last thing you want is for these particles to simply settle down, and when they settle down, they'll form a cake, and therefore if they are substrates or things which are needed by the organism, then the organism will not be able to get at it. And in general, what you want is a homogeneous environment throughout the vessel. And to maintain this, you need to what you call as mix it up. Okay, and agitators are sometimes also referred to as impellers or mixers. Okay, now there are several types of agitators that you can get. You can get what are called as disc agitators or disc impellers. You can have what is called as vaned disc type of systems, and you can have what are called as propeller type of systems. Okay, I'll give you a feel for them a little bit, but a couple of them are shown here. This what you see, no, where the thing is going to rotate like this, it is going to take this paddle and push the liquid along with it. This type of mixer is referred to as generally a vaned disc or paddle type of mixer. Well, if you look at this, where the blades are at an angle, okay, so this is a very nice example of a propeller type mixer. Okay, but here is a nicer picture so that you can get a feel for it. Excuse me. So the flat disc type agitators, as they are called, okay, they will have something like this. Okay, so if you look at the side view, this will be the central shaft. Okay, so here is the shaft, and this thing is going to rotate in this fashion. And when you look at it from the top view, you'll see somewhat like this. There will be little blades, and these blades are going to rotate clockwise or anti-clockwise, mixing the medium. This is very similar to the fan in your house, okay, where you have a very slight angle on the blades, and when you kind of turn the switch on, the fan starts to go round and round, and it mixes up the air which is there in the room and give you a feeling of what are called as air or breeze flowing. This is a vaned disc. So if you look at it from the side view, and this is where the shaft is, you will find now the mixing element is a flatter and a longer, entity. Okay, so if you look at it from the top view, it will look somewhat like this, but these blades are actually going to reach down a little bit. So this is a little bit like your, in olden days, I don't know whether you know, they used to churn your buttermilk to get butter in a little vessel, where they used to put this wooden ladle, and the person who's going to churn will take a little rope which attaches to this ladle, and they'll go back and forth, and mix it up so that the the fat comes up and you get what you typically call ghee from that. Okay, so that type of mixing is called as a veined dish. Okay, so it will be looking somewhat like that. Okay, so the mixing is more efficient than if it were simply flat. Okay, and the third is what you call as marine propeller type. Okay, this is very typical to the propellers you see in the ship, which are at the back of the ship, which propel the ship forward by pushing the water back. Okay, and generally these are the most efficient. Okay, now this third one, which is called as open disc type with a variable pitch, that means this angle can be moved so that as they say, you can get different angles and that pitch will ensure how efficient the mixing will be. Okay, so we have all of these designs which are available in order to kind of mix up the medium. Okay, they are very similar to what you see around in your house, like a fan or that little thing you use to churn up your buttermilk, or things which you have seen in the movie Titanic when it is sinking, like your propeller. Okay, now when you try to mix medium, one of the things that you always worry about is that if you mix too efficiently, you actually will get, rather than turbulent flow, what is called as laminar flow. Okay, and observe this. When you were little, no, or even sometimes at this age also, uh, when you are told to take a bath and they gave you a bucket of water, as a child, you would put your hand inside the bucket and you will, mix the water and make it go round and round. Okay, and you will do it very fast to the point that the center of the water will start to kind of make a little what you call as vortex and the water will be moving very fast, and then what you will do is take out your hand and put a little boat or a duck or something and see the duck kind of go round and round. Okay, and this is a game we all used to play when we were little. Okay, but you have to realize something. When you do this and your flow is very, very fast and very, very efficient, then two entities which are in the water relative to each other will keep on maintaining the same distance as the water is going round and round. When this happens, even though you are churning the water at a very high speed, the efficiency of mixing is very bad because two things are never able contacting each other. Okay, so you have attained what is called as flow, but the flow is laminar, and laminar flow is not very good for mass transfer or heat transfer. Everything in that water will maintain that position, and you'll never get what interaction between each other. Okay. Now, as opposed to that, when you were little, if you remember, you always also used to do some very interesting thing. First, you would mix the water so that it go round and round, and then again, what you do is dip your hand and make the water go the other way by pushing your hand the other side. Okay. Essentially, when you do that, suddenly the laminar flow becomes very turbulent, and that is what baffles do. So baffles are typically things which are put on the side of what is called as a fermenter, and their job is only one thing. When the liquid is being moved, that before the presence of baffle, the liquid will always hit the baffle and then it will come out like this and create what is called as turbulence. Okay, and what this will do is prevent what is called as vortex formation and prevent what is called as laminar flow and ensure that the mixing efficiency is much higher. Okay, so typically you will find anywhere from 2 to 4 baffles always on the side, and the idea is to reduce vortex formation and improve mixing efficiency. Okay, and in terms of size, they are usually 1/10 of the vessel diameter and attached radially. Okay. Now, this is for agitation. Now, for aeration, you use what are called as spargers. Okay, spargers are devices, as I said, to introduce air into the fermenter. And there are three types of spargers typically. What you call as orifice spargers, porous spargers, and what are called as nozzle spargers. Okay. Now, I'll give an example of what is a orifice sparger. Orifice sparger is like if you're in the garden, for example, no, if you watch some movies where they show you people watering the garden with a little device, you'll find that It's like a bucket-like thing with a little spout, and the spout has holes in it. So you fill your container with water, and when you tilt it, water will come out from the end in streams of 4 or 5. Okay, so that type of way of introducing air into the medium is referred to as what are as orifice spargers. Porous spargers are those devices where there are so many holes that when the air comes out, it comes out almost like very fine bubbles. Okay, to give you an example of a porous sparger, no, sometimes you'll find that you can buy those little devices which you can put on taps, and they say that this will filter all the kachara from your water, and they appear to be like a little bulb, and when you attach it to the tap and when you start off the water will actually come out making a big sound like a swoosh, and there will be a lot of bubbles in the water. Okay, so that type of sparger is called a porous sparger. You see that even in your fish tanks. If you have a fish tank, if you start the water, you'll find that you'll come in very fine bubbles as if it is just bubbling out of that little sparger. Okay, so that type of device is called a porous sparger. And a nozzle sparger is just like a big pipe from which water will come out in large bubbles. Okay, so basically, porous spargers produce very small bubble size, and they're difficult to clean. These are orifice spargers are perforated and arranged below the impeller. They generally don't clog very easily. And nozzle, as I said, is a big partially closed pipe which never gets blocked. Okay, there are other variations to the design, but generally what you'll find is these three are the most common. Okay, typically what you'll find is the air bubbles are the smallest in the porous sparger. They are biggest in the nozzle, but in the same way this is more amenable, more susceptible to clogging, while this will never clog. So the point is which one to use. Whenever you are passing air through the medium, there are two things you try to achieve. One, you make sure the air bubbles are as small as possible. And the reason for that is smaller the air bubble, larger will be the relative surface area. And when the surface area is more, the exchange of oxygen which is present in the air bubble with the liquid will be more efficient. Okay. And the second thing you try and do is make sure that the air bubble spends as much time as possible in the medium before it escapes from the surface. Okay, which gives more time for all the oxygen which is present in the air to be taken up by the liquid. Okay, so generally when we do this design of the sparger, we have to make sure that we combine it with the fact how agitation is also occurring. So that the idea is, on one hand you introduce air through the sparger, but then you mix the medium in such a fashion that the air bubble will never take the clean straight route to the surface, but will kind of go in a what is called as back and forth manner through the liquid and then reach the surface. Okay, so basically I do not want the air bubble to come out and then simply go straight up like this to the surface. That means the residence time is very less, but what I want is the air bubble to come up and then take what is called a tortuous path. Okay, back like this, like this, like this, and then finally rise and go to the surface. Now this path, which gives more time for the air bubble in the medium so that exchange is better, is accomplished by suitable design of an agitator and having what is called as turbulent flow. Okay, so many times this aeration system and agitation systems are designed keeping the requirements in mind in a combined fashion rather than in a standalone fashion. Okay, so aeration, agitation, and baffles are many times kind of looked upon as one factor, which has to be optimized when you try to what you call optimize the way the fermentation is going to be done. Okay. Then the other thing you have to remember is many fermentations are very sensitive to temperature, okay, and pH. Okay, and in this regard, you will find that there are two types of fermentations. One, where you need to maintain a temperature, but if the temperature goes, plus or minus, maybe 4 or 5 degrees, it doesn't do too much. But anything more than that, it starts to affect the fermentation. And there are other fermentations where you have to maintain even the temperature to within a degree to get efficient production. Okay, so there are how much you need to control the temperature would actually depend on the organism you are working and the process you are doing. Sometimes very stringent controls are needed, and sometimes a little lax control, okay, with a little more window is permitted. Likewise for pH, there are some fermentations where the pH has to be X plus or minus maybe 0.2 or 0.3. And if you go beyond that, your productivity is affected. And there are other fermentations where the pH can be maintained within say 1 or 1.5 units, and it doesn't do too much to the yield. And anything more than that, then it starts to affect the yield. So again, just like temperature, the pH control required might be very rigid or very strict versus a little more lax. The third thing that also affects fermentation is the fact that a lot of the media that you use for fermentation is rich in protein. And when you are doing aeration and agitation, what happens is the medium starts to foam because of the protein which is present. And if you do not control the foam, what happens is the foam will get into every nook and cranny of the fermenter. And not only that, it will get there along with the medium, which is rich in sugars and protein. And then later on, after the fermentation is done, cleaning becomes a mess. And if you don't clean correctly, then these are pockets where organisms continue to grow, and it might be very difficult to then remove them or completely make a fermenter free of them. So controlling the foam is very important. The second thing is, if there is lot of foam, that affects the way your air exchange or exchange of nutrients also occurs. Okay. Now what will happen is organisms will start coming out of the medium. They'll be present in the foam. Components of the medium like suspension, suspended nutrients can also come as become part of the foam, and it becomes a lot very messy. Okay, so one other thing which is very important when you do fermentation, especially on a large scale, is to make sure the temperature doesn't go haywire, pH doesn't go haywire, and the foam is always kept in control. Okay. Now, typically, what you do is when you want to monitor temperature, you use what are called as thermocouples. Okay, and these thermocouples are placed correctly on the fermenter body, typically dipping into the medium. Okay, and so that you can read the temperature of the medium, because that is what is more important. Okay. And once you sense the temperature, the signal is sent to the temperature controller. Okay. Now, what you do with respect to the temperature controller is set what value you want, plus or minus the value that you can allow the temperature to fluctuate. And then what you do is you set the system so that if the temperature goes beyond this range on the higher side, then cool water will start flowing into the jacket to cool the fermenter. And likewise, if the temperature falls below a certain range, then you start to put hot water or steam into the jackets to start heating the fermenter. Okay, and again inside there are agitators which will mix, and therefore you will be able to maintain the temperature. Okay, so as I said, this water jackets and coils become very important again, therefore, because that is where you will pass the water and cold water and steam from. Okay. So again, as I said, some of them, if you remember, organisms are very rigid. When you do that, then your reader also should be very accurate and should be able to read temperatures which are very close to each other. Okay. Most of the time, you'll use what is called a stainless steel sensors, because we are dipping it into the medium. You don't want to put things which are corrosive. We can easily get corroded, or which are affected by liquid flowing through over them. Okay. There are various varieties of thermometers available, but by and large, the ones which are used are generally made of stainless steel. Okay. The other thing that you monitor as I said is pH. Okay. And here again, you use sterilizable electrodes, and the electrodes are also kept dipping into the main fermenter and the liquid, so that you can measure the pH of the liquid. Just like your temperature controls or temperature sensors are attached to a control panel, even the pH sensors are attached to a control panel. Okay, and there also you set the pH range which you want to maintain. And if you find that the pH goes above that range, then this controller will start putting acid into the medium to bring the pH down. And likewise, the pH falls below a certain range, you start adding alkali to bring the pH back to what you want. Okay, and that is also very crucial. Okay, as far as the fermentation. When you have some fermentations which are aerobic, where the level of oxygen is also very important, then you have what is called as dissolved oxygen probe. Okay, and what these will do is actually measure the oxygen content of the liquid. Okay, or what you call as oxygen saturation. Okay, nowadays we also do that for COVID. Remember, they have a little sensor they put on your finger, and they find out how much is their oxygen saturation. Okay. Similarly, I want to know the oxygen content of the medium so that I know that there is no deficiency of oxygen. Okay, and that measurement is done by what I call as oxygen probes. Okay. Then we have foam, which is also very important. And as I said, foaming is not a good thing because one, it creates a lot of problem of contamination of parts of the fermentator which are difficult to clean, and second, it affects what is called as a heat transfer and mass transfer. Okay. Now you can remove foam in two ways. Okay. One, what is called as use of chemicals or anti-foaming agents to remove the foam. Okay. Uh, Now, when you talk about adding anti-foaming agents, you can have anti-foaming agents which are of different types. Okay, some of them are very costly. For example, silicones and polyether. Okay, and the reason they are costly is one, they are not affected by sterilization. So you can add these anti-foam agents to the medium when it is non-sterile and then sterilize it, and then we can also sterilize them separately and then add them to medium which is sterilized when you want to add them during the actual process. But very more important is they are inert and they don't get metabolized by the organisms, which means when I add these silicones, the silicones will only do the job of anti-foaming and they are not substrate for the organism and get converted to things which are undesirable, and many times they are not even toxic. So they have got very good properties. They are safe to use, they don't affect the organism, they are not metabolized by organism, they are sterilizable, and because of all this they also are expensive. As opposed to that, you can also kill foam using a lot of oils and fats which are available naturally, like peanut oil, soya bean oil, and so on and so forth. So when you put oil into the medium, it will kill the foam. But the problem with these type of systems is, remember, they are unstable. They can get rancid, so they get chemically converted. The other thing is when you put them in the medium, they get metabolized by the organisms and they will generate metabolites which are acidic and they will change the pH of the medium. Okay, and because of that, they are not used when the product that you are making is very high cost product and requires lot of care. Okay, but if you are making things which are for general use, okay, generally non-pharmaceutical compounds and stuff like that, then these anti-foaming agents are used because there and a little bit of metabolism and all doesn't matter to the overall product that you are getting. Okay, so depending on your process, you can use what are called as inert anti-foaming agents or what are called as crude anti-foaming agents. Inert are silicones and polyether, and crude are oils, fats, and many long chain alcohols. Okay, and these you have to use very carefully. Okay, now in addition to this, you can also kill foam mechanically. Okay, for example, above the medium. Okay, let us say you have a big container and the medium is up to 60% of the height of the fermenter, and above that is where the foam will start to build up. So what you do is, above the level of the liquid, you put what are called as discs or propellers or brushes, which as soon as the foam starts to be generated, will hit the foam and break them, or physically kind of break the foam. So this is like what we do sometimes at home. Uh, 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 when you have some foam at the surface of a liquid, we take our fingers and just hit the foam and try to take care of the foam. So that is one way to physically take care of the foam. Okay, and sometimes what people will do is use ultrasonic waves to break down the foam bubbles so that the foam is controlled. Okay, And just like you have detection of pH and temperature and oxygen, you also have foam detector. So what typically you will do is have a foam detector, and if foam is detected, that will trigger the addition of these silicones or oils, or it will trigger this mechanical anti-foam devices, which will start affecting the foam or reducing the foam. Okay, so all these collectively work together. And the last one is what you call as visualization ports and other control systems. Okay, which are also very important. Okay, to give you an idea, uh, when I'm doing a fermentation, typically I have this huge fermenter. Things are happening inside. These are my stirrers. This is my sparger. This is my inlet for air. Okay, inlet for sterile air. This is inlet for steam. I have got ports to add things like alkali, acid, anti-foaming agent. But I also have this little glass thing. Okay, you see this little thing here. I'm able to actually see the fermenter from here and look at it visually. Sometimes this is very important because people who do fermentations for a living, they can actually look at the fermenter and tell you whether things are going correctly or not. Okay, so and this is very important to make sure that you know things are under control inside the fermenter. If everything is closed and I can't even see inside, and I have to rely only on this measurement, they will tell me a few things. But sometimes, as I say, seeing is believing. बोलते हैं ना, a lot of big fermenters generally will have a little port so that you can always take an eye on the fermentation. Okay. In addition to this, things which also impact fermentation and the fermentary processes, where your plant is located. Is it near all the things which are needed for the fermentation? Is it in a remote area? Do you get skilled labor? Okay, so that people can work efficiently and you get skilled people to work. Okay, for example, if I'm doing fermentation where I'm making say growth hormone, and I need to use animal cells, grow animal cells, and then produce growth hormone in them. Then if I'm doing this in a very remote area, I may not find people who are well versed in working aseptically, okay, and maintaining sterility. And it might be difficult to train those people because they might not have the appropriate background education. So many times, these other factors, okay, where your factory is located, where do you have access to all the raw materials that are needed? Are you closer to the port so that you can take the finished goods and export it or take it around the country efficiently? Can you get cheap labor? Can you get skilled labor? All these also become very important as far as the overall fermentation process is concerned, and how basically a fermentation process will be designed. Okay. So after looking at all of these factors, okay, now what we are going to do is kind of get a feel for how the fermenters actually look. Okay, we have been talking about them, and I gave you the first look at a fermenter. Okay, so if you look at the fermenter, pay attention to a lot of things. Okay, so I'm going to start from here. So this is they say it shows there as steam. Okay, but this has two purposes. Okay, you see this valve here. This is actually the what you call an outlet valve. Okay, so after the fermentation is over, I simply have to open this. When I open this, all the liquid will come out, and I'll be able to drain the medium very easily. But this also does one other function, and that function is that I can also periodically sample my liquid to monitor how much product formation has occurred. Okay, and in order to sample very efficiently, what I do is have steam come through, and when steam comes through, what happens is it sterilizes this region. Okay, it makes this region clean and free of organisms. And then what I do is close the steam, open this up, drain a little bit of liquid to sample, quickly close it, and then again pass steam and keep this area kind of clean and sterile. Okay, that's why we put it as steam. This is where sterile air is coming in and it is going into the sparger. And from the sparger, you can see this air bubbles coming out, and these air bubbles will be stirred by the stirrer so that they don't go straight up and they'll take a tortuous path. Now look at this nice stirring assembly. There are three levels at which we have what are called as impeller paddles. So collectively when they move, you will get very efficient mixing. And typically you'll also find baffles on the side. Sometimes they might not show the baffles. So this is cooling water. or you can also have steam coming in. It will go to the jacket so that you can cool or heat the medium. Okay. Then typically what you'll also find is that somewhere in this liquid there'll be a probe for monitoring pH, there'll be a probe for monitoring temperature, there'll be another probe for monitoring oxygen, and there might be a probe up here to monitoring whether foaming is occurring. And all these will be attached to all these control systems so that you can put acid, alkali, foaming agent. And here is an exhaust for air. Okay, so because if you are doing aeration, air is going to come in, the pressure will build up here. So if you don't have a vent, your fermenter will simply burst after a while. Okay, so you need to have a little vent here, and that is a pressure control vent. So the pressure builds up a little bit, the valve will open, the air will go out. Then it will just close up again. When the pressure will build up, this valve will open, the air will go out. Okay, so just to give you a feel for how complex this is, in fact, a lot of parts are not shown here. Okay, okay. So let us get to the main thing. Whenever you doing a large scale fermentation, as I say, the heart of the process is a main fermenter body. Okay, usually it's a big stirred vessel, and as I say, the height to diameter ratio is typically 3. Okay, for example, if I have a vessel which is 10 meters high, I'll usually the diameter will be 3 meters. Okay, so that the ratio is about 3. The volume can be anything depending on what volume you are working in. But generally, when you're operating the fermenter, you'll find that at the most it will be filled 80. Okay, and this is also a higher number. By and large, 65 to 70 is what the filling is. The reason you leave the top portion is so that you can control the foaming. Otherwise, there will be too little space, and little bit of foaming will create a lot of problems. Okay, in that there will be biomass. Okay, and when the fermenter is working at highest capacity, okay, you can have as high as 100 kilograms of dry weight of organisms growing per meter cube. Okay, just to give you an idea, cc cube or centimeter cube is what is called as ml. Okay, and decimeter cube is what is called as liter. Okay, so we are talking meter cube, so it is about 1000 liters. Okay, if I remember right. And the product that you get typically on a good day will be in the range of 10 milligram per liter to 200 grams per liter. Okay, but by and large, you'll find that many products which are produced closer to this end rather than this end. Okay, only a few products which give very high yields like 200 grams per liter and all. Okay, but by and large, many antibiotics which we are talking about, insulin, etc., are at this low end. But that is good enough. Okay, so what are the things that we need from the main body, or what you call it a fermenter? The first thing is it should be strong enough to withstand the pressure exerted by the large volume of liquid. Okay, and you can imagine when I have a container which has got 500,000 liters or 1,000,000 liters or 1,000,000 liters of liquid in it, the amount of pressure it exerts on the walls is tremendous. And then therefore the material which I use to make the fermenter has to be strong enough to withstand this pressure. Okay, so if I use things like copper, which are very malleable, ductile, they will simply bloat up. I cannot use a lot of plastics because they will simply expand under that much pressure. Okay, so the material that is used is in the olden days it used to be iron, but because iron leaches a lot of ions into the medium, nowadays we don't use, and because iron also tends to rust. Okay, unless you use a very specific type of iron which is non-rust iron, most of the iron is amenable to rusting. So nowadays you'll find most of the fermenters are made of stainless steel, especially when you want to work with large volumes. Okay, and the stainless steel is good enough. It is usually corrosion free. It also leaches very little into the medium, and it has the appropriate strength to withstand this much pressure. Okay, as I said, you should not have something which is corroded by the fermentation process, and it should not leach toxic things into the medium. And that's why people do not use things like aluminum, copper, bronze, etc. for fermenters. Okay, because these things tend to leach a lot of ions into it. Stainless steel is the other thing is this fermentation should have adequate provisions for control and prevention of growth of contaminating microorganisms. Okay, and which indirectly means that if I want to do a sterile fermentation, my fermentation has to be designed so that I can work in a sterile environment. Not only that, if it is aerobic, then I should have a provision for air, a sterile air to be passed efficiently into the medium. Okay, and not only that, excess air which is pumped in and CO2 which is many times produced by the organism should have a means of being vented out of the fermenter. Then as I said, stirring is necessary for mixing the medium and also mixing air. Okay, you should have anti-foaming agents. You should have temperature control. Okay, I should have systems for aseptic withdrawal of culture so that I can measure how my fermentation is going on, and again detection of pH. So these are all things we just talked about. Okay, and just to give you a feel for what we are talking in terms of a requirement, I have shown here a very nice picture here. This is one of the largest fermenters in the world. Okay, and it is the fermenter at what is called the Imperial Chemical Industries factory in the UK. Okay, to give you a feel for how big this fermenter is, one is look at this is a vehicle. This is like a SUV almost, which is sitting here. Here are a couple of people who are walking around, men. Okay, and to give you a feel for how big this is, look at the dimensions. Okay, at this point it's about 11 meters. Okay, down here it is around 7 meters, and if you look at the height, it is about 60 meters plus 10. Okay, so it's close to what is called as the 7 to 10 meters in diameter and about 70 to 80 meters in length. Okay, in fact, if you look at all the other accessories which are needed to hold it in place, the length actually becomes close to 100 meters. Okay, and this is that fermenter as it was taken before it was launched, what do you call as commissioned by straightening it up. So this was being pulled, and later on down where the location, at the location, this will be taken up and kept up as if almost like it's a shuttle. Okay, so this is one of the largest fermenters. So you can actually try and calculate what the volume will be. Okay, so get a feel for it. Diameter, take it as around 8 meters. Okay, and the height when it is filled with liquid, presume it to be about 60 meters. Okay, and calculate the volume, and we'll look at the feel for that volume when we actually uh, uh, realize at what level we need things, at what level we need to aerate things, at what level we need to make sure mixing is turbulent, and so on and so forth. Okay. And now this fermenter here, if you look very carefully, has got no mixing elements. Okay, so this is a fermenter which is different from the fermenter which we actually saw earlier. Okay, here you have little mixers and all in the middle. If you look at this fermenter, no, you will see that there is a actually just a second. There is no mixing element. Okay, so this is an example of what is called airlift fermenter. Okay, we'll look at what airlift fermenters are next time. Okay, so what I'm going to do is actually stop here at this point, and when we meet next time, we'll look at the different types of fermenters. Okay, mechanically stirred fermenters or airlift fermenters, and we'll look at a couple of industrial production of chemicals like penicillin. Okay, so I'm going to stop here for the moment. I'll stop my sharing and leave it open for questions. Okay, so let me see if there's anything in the chat box. Okay, just a second. I'll okay, chat box. Okay, first question. We can use immobilized cells for fermentation. Okay, or every time new cells or bacteria are used. Okay, large scale fermentations are of both types. There are some fermentations which are done using organisms which are non-immobilized. Okay, and this is so when the organism is cheap to get. Okay, it is not too costly. For example, if I am doing production of alcohol using yeast, yeast is so easily available. It doesn't cost too much. That I can actually use new cells every time. Okay, but let us say I'm doing a fermentation where the organism that I'm using or the biological system that I'm using is more costly. Then I might not do what you call as a fermentation where every time I have to add new cells. I might actually use the immobilized system. Okay. Uh, After the process is done, how is the media uh, byproducts and waste products disposed of? Okay. Now, usually after everything is done, and as I said, if you're doing 500,000 liters of fermentation, after you get your product, the waste that you generate will be one 500,000 liters ka remnant. Okay, and plus you'll also generate other waste based on washing the fermenter and everything. Okay, now these waste cannot be disposed directly into the environment because they can be harmful, they can be toxic, and therefore you need to do what is called as waste treatment. Okay, you have to do a treatment of the waste with using chemicals or using other microorganisms such that the waste you now have is easily disposable into the medium. Okay, and this is where things like wastewater treatment, solid waste treatment, gaseous waste treatment, all these things come into play. Okay, and you see that happening even at your home nowadays. If you remember, in many localities, they have now started to collect waste, household waste in two different forms. What you call as dry waste and wet waste. Okay, the idea is to process them in such a fashion that they do not cause a problem to the environment. Okay, and similarly to that, even after fermentation is done, you do a lot of very specific treatments to the solids and the liquids that you have generated so that they are made safe and innocuous before they are disposed of. Okay, and this is typically referred to as wastewater management or wastewater treatment or solid waste management or solid waste treatment. Okay, those are topics on their own. Okay, and here is where things like biological oxygen demand, chemical oxygen demand, and treatment, wastewater treatment tanks, etc., come into play. Okay, you are right. I just can't throw them just like that. I have to make sure I treat them very specifically. Then only I can dispose them. Okay, does that answer your question, Aditi?
Yes, sir. Thank you, sir.
Okay. Any other question? Any other question? Okay. If not, as I say, happy Onam to all the people and to all the others. Today is the last day, right? Visarjan ka din hai, right? So Ganpati Bappa has come and gone. It's end of the month. The good thing is it appears that things are loosening up and we might be getting unlocked slowly and steadily. So hopefully at some point we'll see each other soon. Okay, till then, bye. So I'm going to stop recording and
Thank you so